for the invitation. Okay, guys. So yeah, thanks for the invitation. Yeah, I'm looking forward to this talk. I think we come from a bit different communities, so it's different for me difficult for me in advance to know like what will be new to you, what will be completely known to you. So there will certainly be things you've heard before, but maybe others you haven't. So it's a bit of a mix of sort of basics and then things I have done that you probably aren't aware of. Okay, well then I'll jump into it, and actually I'll start with a little story. So I'll try out a little story for starters. So this is about a football match. So this is Granada versus Barbados in the 1994 Caribbean Cup qualifiers. So it's a bit of an urban myth actually, but anyway. So Barbados needed to win by 2 goals in this match, and they had sort of special rules in their tournament. So the first special rule was all matches would go to overtime. There were no draws. And then the second special rule was that there was a golden goal rule. So if you scored in the overtime, then the match would be immediately over. And to spice things up a bit, that golden goal would count double, which is a very unusual rule for soccer. And now I'm going to tell you a story of how that match then turned out. So, as I said, Barbados needed to win by a margin of 2 goals. And actually, things started fairly well. They scored in the 10th minute. Actually, we don't know who scored. That name has been forgotten. And they also scored in the 60th minute. And then there were 2 goals ahead, which obviously was great for them because that's what they needed. But then, unfortunately, 7 minutes before the end, Grenada scored their first goal. And then, obviously, Barbados was in trouble because they need to win by a 2-goal margin. And then at some point, they were like, yeah, we are running out of time, but maybe we can just go to overtime and score that magic double goal. So in the 87th minute, a man called Seeley scored an own goal. And then they essentially had 3 minutes left in the match. And the folks from Grenada were like, yeah, actually, I mean, we'd be perfectly happy to lose by 1 goal margin, then we would qualify. But we'd also be perfectly happy to win 3-2. So they essentially, like, scoring on either end of the field would have been fine for them. And that's what they tried, and it ended up in a very bizarre situation. They ended up not scoring during these regular 90 minutes. And then in the 117th minute, a man called Thorne actually scored this double goal for Barbados. So that's a strange little story. Why am I telling you this? It's because this talk is going to be about rules. And I just wanted to illustrate that strange rules will create loopholes and strange incentives. And strange incentives will lead to strange outcomes, like a football team trying to score on either end of the pitch. And my entire point of this talk will be that choosing rules is important, and that one always has to think about the incentives one creates when choosing these rules. And I think this story maybe nicely illustrates it. You'll tell me whether it made any sense to you. So the rest of this talk is not going to be about football rules. It's about rules for forecasting exercises or challenges or competition or whatever you'd like to call them. And in particular, infectious diseases, because that's what I work on in terms of field of application. So yeah, this forecasting business in infectious diseases, I know this last couple of years, obviously this has become very popular, and people have been doing it for a bit longer, but not that much longer actually. Like in the mid-2010s, people started to work on infectious disease forecasting. For influenza first, there was a large challenge run by the US CDC, which is called the flu side challenge. And then there were a few like smaller challenges over limited time periods on Ebola. You may remember in the mid-2010s, Ebola was a big thing. And then dengue, chikungunya, these kind of topical diseases. And then with the onset of the COVID-19 pandemic, all of this became sort of a big thing, and a lot of people got involved. And there were various platforms. I'll show a few screenshots. So this is sort of what the early efforts on flu looked like. So people tried to predict influenza-like illness in the US. They had different things they were trying to forecast. So a couple of weeks ahead, 4 weeks ahead was what they were doing at the time. And then they'd also tried to predict season peak timing and the hype of the season peak. That's what people were trying to do at the time. And then obviously with COVID, as I said, this all became a lot bigger. People were then also focusing on maybe 1 or 2, even 3 or 4 weeks ahead predictions of cases, hospitalizations, deaths, these kind of things, using a lot of different models. that came from different independent research groups, and then sort of averaging that together into an ensemble forecast. And these things have essentially been running ever since. I'm not entirely sure whether the US has shut theirs down. I think they only do hospitalizations these days, but yeah, it has been running for pretty much 3 years. In Europe, there has been a parallel effort run by the European CDC, which looks pretty much the same kind of dashboard, different models trying to predict the same thing. And then maybe to mention one, I mean, I've been involved also in these two forecasts after I just showed that this is something I actually led over the last 2 or 3 years. For Germany, we've worked on hospitalization nowcasting. So we have sort of a weird hospitalization indicator where in the end, we always have sort of an artificial downward turn where we know that this is just due to the fact that data are delayed and are not complete yet. And then the last couple of values are not reliable. And we always try to predict what the actual current trend is looking like, anticipating by how much these data are still going to change. And yeah, then at some point, we obviously have the revised data. And in this case, we could see that it worked fairly well. So these are a few settings, let's say forecasting challenges that have taken place in the past in infectious disease epidemiology and that I've been involved in. Another example, and I'll get back to those in various examples. And another example, not from epidemiology, but from the social sciences, actually, that I'll get back to later, is the views forecasting challenge. That's a challenge where people try to predict armed conflicts. So for all African countries, they sort of issue predictions on how likely it is that there will be a certain number of deaths from armed violence. Okay, so these were sort of application examples that I'll also get back to later. And my role in the projects that I've been involved in has usually not been issuing forecasts, even though every now and then I also issued some forecasts, but evaluating these forecasts. So obviously, when we forecast something, we can observe what actually happened later on, and it's a good idea to try and compare what happened and what had been predicted to get an idea of how good we are at forecasting, whether we should pay any attention to these forecasts and so on. And in a way, there are two ways of approaching that problem. That's what, in our community at least, we call absolute forecast evaluation. So the question would be, are forecasts any good? Essentially, we would check whether they are statistically calibrated. So for instance, do 95% prediction intervals cover the observations in roughly 95% of the cases, questions like these. And then there is relative forecast evaluation, where you have different forecasting models, and obviously you have the observations, and you want to see which models are maybe in better agreement with these observations. And in the end, you're trying to rank these forecasters according to their predictive performance. And that is usually done using scoring rules, and that is going to be the topic of my talk. So I'll spend 95% of my time today on relative forecast evaluation. Okay, so I'll start with sort of a simple setting, which is point forecasting, which is helpful to get across a few central concepts to think about scoring rules. So I think these are things that you're certainly familiar with. So we have different ways of measuring the quality of a point forecast. You could think about absolute errors, or absolute percentage errors, or squared errors. And essentially, we call all of these scoring rules. A scoring rule is something that takes a forecast in any format, could be a point forecast, or later on an interval forecast, or a probability distribution that represents a forecast, and then it takes an observation and returns some numerical value, where as a convention, we'll say that lower scores are better. So we always orient things in a negative way. Okay, so these are different scoring rules for point forecasts. And now one really useful concept to think about these different scoring rules, and as you may remember, I said that I want to talk a bit about the incentives created by scoring rules, is the so-called Bayes Act. And I'll try to get across what that is. I assume a lot of you already know. So essentially, we assume that even if we are in the point forecasting setting, where people will just need to report one number that represents their forecast, they actually have some sort of distributional belief about the future, which I denote by F. So that's in our forecaster's head, right? And then there is somebody who is going to evaluate these forecasts, and that person defines some scoring rule that is to be applied. So it could be the absolute error, for instance. And then our forecaster starts thinking, well, given that this is the scoring rule, and given that I think that the outcome comes from a distribution F, what would be the smartest forecast to make? And a smart forecast here just means that he tries to minimize his expected score. So we look at that forecast y hat, which under the distribution F, which our forecaster believes in expectation yields the lowest score, and that is called the base act. And well, then he tells the evaluator about that forecast. Now, what's important to note is that this base act, so BA, doesn't only depend on F, it also depends on S. It depends on the scoring rule. So for instance, if our evaluator had said, I'll evaluate you using the squared error, then maybe our forecaster would have issued a different point forecast, because that would have yielded a better expected score under that different scoring rule. Also, on a side note, these base acts may not be unique. And well, then at some point we observe something, and the evaluator tells the forecaster, well, your squared error in this case was 9. So that's the idea of the base act, and we use that in a couple of contexts. And now there's essentially a duality between the scoring functions and the base act. So as I said, different scoring functions lead to different base acts. And if you organize a forecasting challenge, then in a way you can either choose some functional of a predictive distribution that you might be interested in. You might say, I care about the predictive means of my forecasters, and then you should you should use for instance, the squared error is not your only option, but you could use, for instance, the squared error to evaluate forecasters and incentivize them to actually tell you about their predictive means. Or the other way around, you could say, well, my loss, let's say my utility, is well reflected by a squared error, but then you should also note that, well, in that case, people will tell me about their predictive means, and that's something worth knowing. And just in terms of terminology, if some functional of predictive distribution is the base act under some scoring function, then we say that that's elicited by the scoring rule, and the other way around, if we say that the scoring function is consistent for that functional. Okay, and now one point that I'm trying to make is that you should always think about these two things. You should think about whether a scoring function is something that is reasonable for you because it reflects how useful different types of errors are, but you should also think about the incentives that you create by using that scoring function. And in practice, I observe that people usually mainly think about whether the scoring function sort of reflects how useful they think different forecasts are in light of the observations, but they don't really think about the incentives. And I think that should be done a bit more. Okay, so just as an example, we had the absolute percentage error as one of these three types of error measures. And here it's interesting to know that if you use absolute percentage errors, you are asking for a type of point forecast that is typically considerably lower than the predictive median or mean of your forecast. So here, for instance, we have that for a normal distribution, which is centered around 20. So the mean and the median are both 20. So if you use squared error or absolute error and your forecaster believes that is the actual distribution, they would tell you 20. But if you ask for, if you tell them that you're going to use the absolute percentage error, they're actually going to tell you 12 rather than 20, because that's sort of the smart thing to do for them under that error measure. To put it more technically, that is the median of order -1 of that distribution. That's the base act under the absolute error. It's a very sort of obscure functional of that distribution. Okay. And I got one little example on that. That's a recent paper that we wrote. So in this conflict forecasting project that I mentioned before, the organizers are using a score which is called TADA. It's a bit of an unusual score that they invented specifically for that challenge, and I'll introduce that to you. So it's defined as follows. It's the sum of two terms. One is just the absolute error, and the other one is this A term here. And what that does is essentially that it adds a penalty to that score if your forecast y hat and your observation y are on different sides of a tolerance region plus minus epsilon that they put around zero. And the intuition is that they want to penalize forecasters that get the sign of the outcome wrong. Because they say in armed conflict forecasting, escalation and de-escalation are such such an important aspect of our forecasting task. So we want to reward forecasters that get that right and penalize those that get it wrong. However, when they then actually evaluated all their forecasts using this score, they realized something very peculiar. And that was that none of their models, very sophisticated models, a lot of different machine learning stuff, also theoretically motivated models that they were using, none of them was able to outperform a very simple forecast, which was just next month is going to be like last month. Nobody was able to outperform that forecast under that score. And I mean, that's something you also see in different contexts. That's actually often difficult to outperform, but they were a bit surprised by that, especially given that under other scoring rules, they were able to outperform that very simple baseline. So they were like, maybe something is strange about this scoring rule. And yeah, that's where colleagues of mine and I came in. So here's just another sort of illustration of what that score looks like. Yeah, I already mentioned that. So it's the absolute error, and then you get an additional penalty if you're on the wrong side of that tolerance region. So that's how it works. And what we did was that we derived the base act under this score. And it's sort of a weird thing. It's like very difficult to see visually what this actually means. So I give you an intuition. Essentially, the base act under that score is that you take the predictive median, but then you shift it quite a bit towards zero. So this score essentially incentivizes you to predict something that's not very far from that tolerance region, which in their case was plus minus 0.05. So essentially, it discourages informative forecasts, let's say. It encourages people to just say next month is going to be like last month. Here's a little example. So if this is your predictive distribution, then your predictive mean, which you would report under squared error, is this guy here. And if you were to report your predictive median, so under absolute errors, it's this one here. And then under this tether score, you report something considerably closer to zero. And essentially what happened in their competition was that people optimized their forecasts for squared error, thus reporting things that were far away from zero. And then they were evaluated using a different score that penalized on average forecasts that were far away from zero. And that explained sort of their weird result in their paper. So intentionally, they incentivized issuing only forecasts within or close to that tolerance interval. And I think that's an interesting example of how not thinking about the incentives of a score can give surprising outcomes. Okay. That's maybe enough about point forecasting or life into probabilistic forecasting, which I would argue is more interesting, especially in fields like infectious disease epidemiology, where often there's a lot of uncertainty. And again, we can use that concept of a base act to think about scoring rules. So we are now in a setting where scoring rules will take in one probability distribution, which I called F or G here. And one outcome, and then essentially there is one central property of these scoring rules, which at least in our group we very much emphasize, which is propriety. So we think about the same little cartoon that we already had before. So a forecaster has some probabilistic belief about the future, F, and then evaluator tells him, I'm going to use this and that scoring function for probabilistic forecasts. And then what would, let me put it this way. What would be nice would be if the scoring rule also incentivized the forecaster to tell the evaluator his actual belief about the future. Otherwise, things would be a bit weird, right? In the point forecast setting, there's maybe a debate that can be had as of whether we want to have predictive means or predictive medians, but if we look at entire probability distributions, then we just want to know what the forecaster actually believes about the future, right? And that means that we would like the base act under a given scoring rule to be the same distribution that a forecaster believes in. If instead the forecaster were incentivized to issue some other predictive distribution G rather than their true F, that would just be strange, and we would not learn what the forecaster actually believes in. So propriety, in a way, encourages honest forecasting. It just incentivizes forecasters to actually tell you what they are thinking. Okay, and one sort of good intuition to think about these proper scoring rules is that they are always about sharpness and calibration. These are sort of two properties that we would like to see in forecast, but it's sort of challenging to have both of them at the same time. So calibration means that that forecasts and observations sort of are statistically consistent with each other. For instance, forecast intervals should cover as often as they're supposed to cover. Sharpness, on the other hand, means that we want forecasts to be informative. So if I just tell you, well, the number of new COVID cases tomorrow is going to be between 0 and 6 billion, that is certainly going to be calibrated in some sense, but it's also completely useless because it's not sharp. So if we think of it again as a little cartoon, then, well, this green thing here, given that black observed curve, would be a nice forecast. It would be sort of calibrated in the sense that it's not off, not wrong. That's maybe not very sharp. So that would have been an even nicer forecast, right? Being even sharper while staying calibrated would have been nice. However, if that forecast had been issued in combination with that observed course later, then, well, while it's sharp, it was just confidently wrong. So that's not very interesting. So we want sharpness only subject to calibration. And if like this happened, the predicted course and this the observed course, then we would actually have preferred a less sharp prediction. So anyway, sharpness is interesting, but only subject to calibration. You should only be self-confident about your forecast as long as you're also right. And proper scoring rules assess these two things jointly and sort of bring them together in one single number in hopefully meaningful way. Okay, and now I'll run through a few of these scoring rules that we are commonly using in epidemiology, but which are also used in weather forecasting, for instance. And one quite simple scoring rule, which nicely reflects this intuition of sort of sharpness and calibration, is the so-called interval score. So this is sort of a simple score in that it doesn't look at the entire predictive distribution, but just at one interval from that distribution, so the 1 minus alpha prediction interval, which reaches from the alpha half to 1 minus alpha half quantiles of that distribution. And then it looks at three things when it checks that forecast against an observation. It looks at the width of that interval. So as the score is negatively oriented and you want to have low scores, it means that you're penalized for issuing a wide forecast interval. That's what's happening here. And then there are two penalty terms. One penalizes you if your observation is below the lower limit of your interval, and the other one penalizes you if the observation is above the upper end of your interval. And then the penalty essentially corresponds to a scaled version of the distance between that interval and the observation. And that sort of nicely illustrates that there's a trade-off between that spread component and the others, because obviously if you issue a wider forecast, you're less at risk of being penalized over here, but then you have to pay over here. So that's a very simple scoring rule, and it's constructed in a smart manner because it's constructed such that you actually have an incentive to predict to issue your predictive alpha half and 1 minus alpha half quantiles. So these different things are balanced in a smart way that creates the right incentives. Few technical side notes. It's proper but not strictly proper, so it cannot really distinguish between different forecasts that share the same alpha half and 1 minus alpha half quantile. one thing is maybe worth noting for practice is that you need to fix that level in advance, so you can't compare interval scores across different nominal coverage levels. And yeah, here's just a reference to some colleagues' work. Here's maybe a bit of an intuition of what that score then does. We here have 1 week ahead forecast of this ILI measure, influenza-like illness in the US, and here's the 80% prediction interval. And here we see what these scores then look like. So most of the time, whenever these observations are inside of the intervals, then the score is purely a function of the width of that 80% prediction interval. And then whenever we fall slightly outside of these intervals, you get penalties which can be quite pronounced that result from that non-coverage. So that's how this score works. And that's actually something we are using in practice as well. Another score, which is also fairly intuitive, I would say, is the David-Sebastiani score. That's another sort of semi-probabilistic score, I'd say, because it evaluates only predictive means and variances. And yeah, you will recognize this. It's a bit like in a density function of a normal distribution, log density function of normal distribution. Essentially, you are penalized for Pearson residuals, let's say, and then there's also a penalty for the predictive variance that you issued. And here's maybe a first little example of what can happen if you use improper scoring rules, because sometimes people sort of forget about this penalty for the predictive variance, which makes the score proper, and they just assess the sum of squared Pearson residuals. And that is improper. There's a really straightforward way of cheating on that score, and that is just to issue very large predictive variances. Because if I issue something really large here, then the entire term will just become tiny, and you can get a very good score using a very bad predictive distribution. So that's why it's important to stay proper and use that penalization here. Okay, and now we go into actual predictive forecasting or evaluation of actual density forecasts, where we use the entire predictive distribution to assess forecast quality. And so the classic here, and you've certainly heard about that, maybe not under that name, but you've certainly heard about it, is the logarithmic score. You could also call it the predictive log likelihood. And essentially, we just assess for each observation, well, how likely was that observation under the forecast distribution that some forecaster issued. This score has a lot of desirable theoretical properties, likelihood principles, so likelihood sort of most powerful in distinguishing different models and so on. So this is a nice score. Maybe a downside is that it's not super robust. So if your forecast was really wrong and maybe it didn't assign any probability mass to where you ended up, then you're sort of in trouble and you can't even really evaluate it anymore. Okay. And another example of what can go wrong, so another improper scoring rule, but that is based on this proper scoring rule. So, and that's something that has been used in infectious disease epidemiology for a couple of years, actually. It's the so-called multi-bin logarithmic score. That was a sort of variation of the log score for discrete outcomes. So they had bins, actually. So they bit their incidence measures, and then they wanted to assess how good the forecasts for these different bins were. And essentially what they did is they used the log score, but they built a tolerance into it. So they said, we count all the probability mass that is in the correct bin and also the neighboring D bins. And that turned out to be not such a great idea. I won't get into the technicalities of that, but this can be shown to incentivize too sharp forecasts. And the intuition is as follows. Let's say we're trying to predict the week when this epidemic is going to peak. So that's another discrete target to which we could apply the score. And let's say this is our actual predictive distribution. Then, actually, in a way, there's no point in placing any probability mass out here for the distribution that you're going to give to your evaluator, right? Because the mass from the neighboring bin will be counted for this one anyway. So I could just move this thing in here, and then it will also count for this neighboring one, and sort of it'll just be smarter to put it towards the inside than towards the outside, right? And actually, so the smart forecast to issue, if you believe in the black distribution, is this red distribution, which just moves everything ever so slightly inside. And yeah, that's what's sort of smart thing to do. And actually, in this little comment that I wrote back then, I showed that empirically you can actually improve upon people's distributions by sharpening them in a smart way that will optimize these scores. So I took the best model from that competition at the time and sort of applied my cheating scheme to it, and it did indeed improve the average quality of these forecasts. But this has been changed ever since, so you can't exploit that loophole anymore. Okay. And then a second scoring rule that is now, so I'd say, predominant in infectious disease forecasting is the CRPS. That's also a score that we've heard quite a few things about in Rogers and Tina's talk last time, and it's what we actually use in practice. So that's the integral over the squared difference between your predictive CDF and a function that jumps from 0 to 1 at the observed value. So what does that mean? So essentially, it's somewhere about this area here. It's actually more about this area because there's the square here. And the intuition in a way is that your CDF should increase somewhere close to where the observation then ended up, because that means that the probability mass was close to that value. And a handy interpretation of that score is that it's a generalization of the absolute error. So that's maybe not super intuitive and easy to see from this formula, but if you draw this graph, then actually it's easy to notice. So let's say that the observation ended up over here rather than over here. Then, well, we just have this sort of almost rectangle that reaches from where the probability mass is to where the observation is, and it has height 1, and then it's just something roughly like the absolute error with respect to the median of that distribution. And if that was just a point mass distribution, then it would actually be equal to the absolute error. So in terms of intuition, you can think of the CRPS as an absolute error that also takes into account the forecast uncertainty, which I think is a like nice intuitive property of this score. Okay, I'll mention that that there's a nice connection between the interval score that I mentioned before and the CRPS, where the CRPS is essentially a weighted average of interval scores at different nominal coverage levels. And that comes in handy if you only have a set of nested prediction intervals and sort of want to make sense of these different intervals altogether. Then you can just evaluate each of them, weigh the results together, and you get something that's very similar to CRPS, which then in turn has this nice interpretation of sort of probabilistic absolute error. And that's how we think of these things in practice. And what's also nice about this alternative display is that this decomposition into a spread component, an overprediction component, and underprediction component that was nicely encoded in this interval score is then inherited by the CRPS. And that's also something we often like to look at in order to learn something about why certain models are maybe performing better than others. So here's just a little graphical illustration of this this relationship between interval scores and CRPS scores. So here we have again these forecasts and observations for the ILI numbers, and this is the same plot we saw before, where we have sort of very abrupt penalties whenever we are slightly outside of these intervals, and most of the time we don't have penalties, but then sometimes we have really strong penalties. And CRPS, as it combines interval scores at different nominal levels, does this in sort of a more smooth fashion, because it applies small penalties if you're outside of the 10% prediction interval, but large penalties if you're also outside of the 95% prediction interval, let's say. And then you get sort of a more nuanced picture where these different components are maybe a bit more smooth. Okay. I'll just show a few slides on how we actually use this in practice, how we would display evaluation results. And I'm using, again, this example from nowcasting hospitalization incidences in Germany, where, as I showed before, we always have these sort of biases in our data and our forecast is just about predicting how the data are still going to be revised. So that's something we worked on for quite a bit. So Daniel is actually on the call. He's the first author of that preprint. And for instance, one display that we commonly use is such a display where we have a summary of the average CRPS scores, and that's decomposed into these different components. So for instance, we would see, well, the KIT model, that's ours. It's sort of okay compared to the others. It seems to have issued wider forecasts, so it has more penalties that are due to its spread, but it's less penalized for forecasts falling outside of these intervals. We could also see, for instance, that all the models all the time get penalized for under prediction and hardly ever get penalized for over prediction. So there seem to be some sort of biases in these different models. And then we complement this with sort of a display by forecast horizon, because we do this for today, but also for data from 28 days ago. And then we usually have some sort of baseline model that we compare things to, and then this, for instance, would mean that, well, this epi-forecasts model has scores that are around 27% of the scores of that naive baseline model, which is really very naive. So that would be sort of how we summarize these things in practice. I think I should note that all the scoring business is very interesting and nice, but you also should just look at what the forecasts looked like. So here, for instance, we have an overlay of the 0-day ahead and nowcasts and the observations, and we can see that, for instance, well, the KIT model seemed to have a bit of an issue with maybe weekday effects. There's this weird periodic structure in them, and maybe some others like LMU, that was just way too overconfident. So I think it's also relevant to just look at plots of the forecasts you've been doing. And then we of course, also assess sort of separate aspects like calibration. Do the different forecast intervals actually contain the observations as often as they should? And they actually don't. Calibration was kind of poor in this forecasting exercise. So most of the time, for most models, the 95% prediction intervals actually covered in more like a quarter of the time, which was a serious issue in this application. Okay. And then actually I'm already sort of approaching the end. One aspect I wanted to talk about, because it links in with the talk we had a couple of weeks ago, is that CRPS depends a lot on the scale of the thing you're looking at. So if you average CRPS scores across different forecasting targets that are in different orders of magnitude, which is usually the case for epidemics because they grow exponentially, then the emulation will be dominated by these forecasts that have been issued for time points when a lot of incidents was going on. So here we have a plot of forecasts and observations, and then down here the scores that resulted, and you can see that the scores that are received for targets where nothing much was going on are pretty much negligible compared to the ones that people receive when something is actually happening. That can be considered desirable. Maybe we would like to have a bit of a more balanced, nuanced view. And one thing that we've argued in a recent paper is that it's maybe much more reasonable to look at log transformed incidences as a forecasting target rather than regular incidences. It's like a very simple suggestion, but it actually has a few nice properties. So one is like a probabilistic relative error. That's sort of just like the regular CRPS is like a probabilistic absolute error. This becomes a probabilistic relative error. And then it sort of makes sense in our field of application because we are dealing with exponential phenomena, and this can be seen as an assessment of how well the growth rate was actually being predicted. And then there's a third motivation, which is actually my preferred one, which is that under certain assumptions, which empirically seem to be approximately fulfilled, this yields scores which are roughly independent of the order of magnitude of the outcome. So the reasoning is roughly the following. If your forecast distribution F is roughly normal, then the expected CRPS value of your outcome, if your forecast distribution is also a true data generating process, is proportional to the standard deviation of that distribution. That is just a theorem that exists in the literature. And it can now be shown that if the mean variance relationship of like say different forecasting targets, you have different distributions for different forecasting targets, and if the relationship between the means of these distributions and the variances of these distributions is quadratic, then it can be shown that the expected CRPS will be pretty much constant across across targets of different orders of magnitude. And now that seems like an arbitrary assumption that this mean variance relationship would be quadratic, but actually it turns out it's not such a bad assumption. I'll start by showing you again this plot of the scores that people observed during different parts of the pandemic, and here that's what we get when forecasting and evaluating on the regular scale, and that's what we get when forecasting and evaluating on the log transform scale, and it looks very much more balanced. Actually, we try to, so that this is slightly hand wavy. This is not 100% convincing, maybe, but we try to assess this mean variance relationship or mean CRPS relationship empirically, and actually it turns out that it's pretty close to quadratic, or actually it's pretty close to a linear mean CRPS relationship, which is pretty close to a quadratic mean variance relationship. So a value of 1 here would imply that this assumption that we made is fulfilled. It's 0.88, which essentially means that if we evaluate things on a log score, we will give slightly more weight to small forecasting targets than large forecasting targets, but it's actually pretty close to giving similar weight to all forecasting targets, which we think is a nice thing. Okay. And then, yeah, a few words about how would I go about choosing a proper scoring rule in practice. Well, hard to tell. Sometimes you're constrained by what you can actually use in the setting where you are. So CRPS requires certain level of scale. Log score is maybe difficult to use if you only have samples. Log score has some nice properties where it's very powerful, but then again, it's sort of sensitive as well, and maybe not very well behaved in settings where your forecasts are not that great, and CRPS may be a bit more robust. Log score is actually scale invariant, so this entire problem that I just talked about would not occur for log score, but it does occur for CRPS. And yeah, I already said that. In general, I think we should not obsess with score-based evaluation either, and also just look at what we can do. Yes, that a few sort of open questions. I mentioned that we usually try to compare things to a simple baseline model, but it's not that obvious what that baseline model should be. So it could be historical averages, could be last observation carried forward, could also be some sort of just simple ARIMA model or something. And the results you present can change a lot depending on what you use here. So that's something I haven't quite made my mind up about. Another thing we often face is that different models have been operated during different time periods, and then it gets difficult to compare them fairly. So if one model, for instance, this one, just missed this entire time period, then it just gets tricky to compare it to this other model, which maybe was not issued here. And that's likewise something that we haven't quite figured out yet. We have some sort of heuristic approaches, but I'm not perfectly happy with them. And then as a last thing, and that's also something that Roger and Tina sort of raised as a general question. We sort of have mathematical tools that ensure honesty, but it's not always totally clear whether they also coincide with what we or especially forecast users would consider high quality, useful forecasts. For instance, here there's another little cartoon. If at this point in time, forecaster green and forecaster orange issued these two curves, these two forecasts, just point forecasts, and then this black curve is what happened, then pretty much all statistical measures would agree that forecaster C was the better prediction. It's better by all the standard measures. But actually, a lot of people would say that forecaster D was better because he sort of captured what the qualitative shape of things would be. So that's something I'm also intending to work on in the future, but where I can't say that I have a very clear idea yet. So yeah, that's what I had to share. I hope it gave you a bit of an impression of what is going on in our field. Maybe you have useful things to tell me that might facilitate my future work. In any case, I'm very much looking forward to the discussion. Thanks a lot.